So our next report from the RCN is coming from Dr. Brooke Meyer from Marquette University, Technological Innovation for Peace Sustainability.
All right, thanks, Jim. So hopefully this is a good follow-up to our last couple talks from Mike and Steve earlier on, as we talk a little bit more about the specific technological innovations. So I'm going to do a little bit of a brief report out and summary of some of the efforts that we've had inside of our group, which really focuses on looking at technologies and how we're moving towards different ones in the future and how we can play off of what we already have. So our group, briefly, we have researchers who are involved in this effort who are across the United States, from Canada, from New Zealand, from Ireland. So we're bringing a lot of perspectives to this issue as we think about how we can better inform technologies and strategies so we can come up with a better and more effective approach to phosphorus management. So from this perspective, we've done a lot of work on the removal and recovery portion of this. So kind of picking up on the last question and some of the themes that we've been talking about today, one of the big things that we've been really discussing as a group, and I'm sure that you all have in your own contexts and domains, is this issue of total value of phosphorus recovery. And so we're well acquainted with the issue that we're looking at trying to close this phosphorus loop, right? We have the phosphorus that's going out into the environment, we need it for agriculture, can we close that system, look at a circular economy? But as we've kind of noted, there's technologies around and we're starting to implement them, but if we look across the wide scale, we still don't have a lot of phosphorus recovery in place. And so one of the major barriers is, of course, thinking about economics of it, and that's come up a couple times. So the phosphorus itself, the product alone, oftentimes can't support the financial burden of putting the recovery processes in place. And it's not necessarily that the processes are really expensive, it's just the cost of the product can't necessarily return on that investment. So this is one of the issues that we've been thinking about and trying to tackle, because we recognize that in terms of products that we see up here, we have phosphorus, but there's also a lot of co-recoverable products, and they've come up a lot before. So we have the nitrogen, we have the energy, materials and minerals, and the water itself if we're thinking about wastewater applications. So these things might have a number value on them, but when we talk about total value, I think one of the really key things is that we also have things that aren't easy to monetize. So value is going to not just necessarily be a number, but also account for some of these services that we can put into place that are going to be helped out by removal and recovery processes. So this total value proposition, I'll probably repeat this a lot, but I think it's a really important message. And so as we think about these global drivers that we've mentioned that are really driving home the phosphorus removal and the recovery optimization, we know that we're tied closely in with energy and food and water. We can't separate them. So even though our forum here today is, of course, focused on phosphorus, I think it's really important to account for all of those other nutrient cycles that have come up in Steve's talk and before. So as we look at this, again, we can't necessarily support the value of the phosphorus as a product alone. But if we combine that with some of the key co-products that we see here in blue, and these could be things like the manure, the compost that have come up before. It could be the water itself. So the water is a really valuable process and product, the outputs of the system. And some of these that are maybe a little bit harder to see, but in here, when we think about these really complex matrices where we might have waste materials that the phosphorus is more or less lost in until we can get it back out, we can also think about other materials that might add value to the system. So in the case of municipal wastewater, there was a study that came out and said that there's actually measurable concentrations of some of these really valuable materials. So in this case, we're looking at gold and silver. So maybe we're not going to get to the point where we mine it, maybe we are, but these things can all start to add to the value proposition as we make the case for why we can co-recover all of these things together. All right, and then in addition to that, we have some of the services shown in the green colors here. So key we know is that we're looking at preventing eutrophication. It's our biggest driver where we have a lot of regulations in place. But there's also a lot of services that we can think about in terms of improving operation. So instead of precipitating struvite in our pipelines, let's make a product that we can actually take out and recover into the market. In addition to that, of course, we're looking at sustainable development goals. So we're supporting food system, and that in turn supports social equity, and so we can follow that down the line as we look at this total value story. All right, so I want to dig a little bit more deeply into some of the technologies that can be used to accomplish these goals of removal and recovery. So anytime we're talking about technology, some of the important things that we want to think about are cost and energy inputs. And so we're looking at cost along the x-axis here, and we have our energy inputs along the y-axis. So makes sense. We want to be down in that far corner in there. We want to minimize both of those things to the extent that we can. And so I have a sampling of technologies here, not comprehensive, but we can see that they kind of group into these locations where down in our far corner in this group 1, we're looking at processes that can extract phosphorus from the liquid phase. And right now they tend to be a little bit on that more cost competitive end. So we might have more common use of them, or they're going to be put into place faster. But the other part of this graphic is if we look at the size of those bubbles, so if we get a bigger bubble, we're going to have more phosphorus intensity in that system. So as we move away from the liquid phase into the sludge itself, or the sludge ash, we actually have higher phosphorus intensity that we can recover. So if we think about kind of comparing all those things in, we want to balance out the costs of the process itself, but also the revenue that we might be able to bring in from getting higher phosphorus intensity. So these things that I've been showing and in this graphic also are really kind of focused on how can we get that phosphorus out of the wastewater, whether it's the liquid or whether it's the sludges. And we can do a pretty decent job at this, and we're continuing to improve these processes. We have a good array of them that have developed over the last few years, and I think these are going to continue to keep evolving over the future, and we can think about how we can best optimize these. And some of the attributes that we can do that with are, again, going back to that enabling co-recovery of other resources, but also continuing to reduce the costs and energy inputs, and then also thinking very much about the product side of things. So we had a discussion at our table this morning about the product end driving the technologies. So we want to make sure that we're focusing on things that have a high purity or a composition that's going to be applicable to different scenarios where it's actually being used. We want to make sure that's manageable also. And the last part on here that I have is that it should be locale appropriate. And I think that can be interpreted a lot of different ways. So we can think about it as a developing country context versus a developed country, for example. So we have an opportunity to maybe leapfrog technologies over what we already have in place in places like the US, and then focus more so on a target of resource recovery rather than solely waste management. So that's one option. Other interpretations of locale is where is that phosphorus? So we're going to get the biggest bang for our buck out of this system. And so all of these things that I show here focus on the wastewater. But I think it's good to think about where is the rest of the phosphorus, right? So if we want to have a very effective phosphorus management strategy, I think it's important not to discount any of our options. And so if we look around and think about where that phosphorus is, it's in the urban sector, it's in the agricultural sector, and it's also in the aquatic system. So we have kind of these three realms that we can consider. So if we kind of trace this down a little bit further and think about where is the P. So in terms of a phosphorus balance. So on this kind of simplified diagram, we're looking at the natural environment, and we know that phosphate's going to cycle from the rock phase to the soluble phase back again, but that happens on geologic timescales. So if we zoom in then on the global food system, we're also zooming in on the temporal timescale. So things are moving fast through the system. We have phosphorus coming in the fertilizer. It's supporting the agriculture and the livestock. That in turn is going into food processing, and then humans eat that and excrete that. So one of the key things I think on this diagram is we're thinking about the magnitude of the phosphorus flows. So that kind of matches up with the size of the arrows here. It's relative terms, but the smaller the arrow, the smaller the flow. So a lot of the technologies that we've looked at in my last slide or two kind of focus in that bottom corner of human excreta. And we can see that we have some good flows there. They're good opportunities because it's a concentrated point source. So it's a way to move forward. But if we think about magnitudes of other flows, we can also start to capture them from other locations in the system. All right, so as we think about all of this and kind of take more of a watershed approach, I guess, for a second, we can think about the phosphorus that's flowing through our agricultural systems, through our urban systems. It's eventually going to wind up in our waterways. And so in thinking of this, we want to account for all of these different types so that we can identify the best opportunities for phosphorus management in variable systems. So some of the key questions that we've been kind of grappling with as a group right now as we address these are thinking about how does the P quantity and the form vary across these diverse systems. So what does it look like in agriculture, urban, and aquatic? And what it looks like then is going to dictate how we're going to best manage it. So number one, for protecting water quality, but number two, can we recover a product that we can use back out of the system? So when we think about those two things, we can kind of subcategorize our management options and technologies, and we can think about, is it ever appropriate to manage phosphorus at the sink rather than the source? And I'm going to come back to that thought in a second. And then also, what are these trade-offs? So what are the benefits and costs of any type of system that we're implementing, whether it's a technology-based or we can think about it in the broader context? All right, so if we go back to our watershed, we can think about kind of the different formats where this phosphorus is coming into play. So if we have, for example, a crop-dominated land, we might be looking at phosphorus in the form of erosion or drainage or crop residue. These are probably going to be characterized by fairly low phosphorus concentrations, but if we think about it on more of a mass balance scale with pretty high flows here compared to some of our urban systems, then we might have a reasonable amount of phosphorus that we can work with and start to tackle some of our issues out of that. All right, on the other hand, if we look up at our livestock-dominated lands, we might be thinking more about manure. And so we've talked about manure already this morning. It's our third product that we have out of our system. And we know that it has a lot of different characteristics from some of the other systems that we looked at. And number one being that it has very high organic content. So organics tell us that we're going to be looking at some energy inputs here. We might have nitrogen, we might have potassium, other things that we can start to use to increase that value proposition. All right, as we move downstream and look at some of our urban, so urban, there's lots of diverse flows in here. They might be the wastewater itself or the products that derive from that, so the urine, the biosolids. We might reclaim that water and use it for landscaping. There's leaf litter, yard waste, pet waste, all sorts of waste in the urban environment. But if we look at all of those different categories, they're very diverse in terms of the amount of phosphorus, the total amount, but also the density of phosphorus and what sort of form it's in. And that's going to dictate then our management strategy. All right, and then all of these sources that we've looked at so far, so where the phosphorus is being generated and input into the system, then lead into our sinks. And so the way we've defined it, we have these sinks are the streams and the lakes and the sediments where the phosphorus winds up. So what can we do in scenarios like this? So a lot of times I think in management scenarios, we tend to think of the sources, and it makes sense, we can apply it right there. But there are certain scenarios where the sink might be an appropriate location to look at. And so that's something that we're considering and evaluating. So one of the examples that comes to my mind is Florida Everglades. So Florida Everglades are really phosphorus sensitive. They have a lot of diffuse inputs into the system, so can't be necessarily well controlled with a point source strategy. So the ongoing Barley Prize is focused on technologies that have an option even of recovering or removing that phosphorus from a natural environment, from lakes and rivers and streams. And another one that's coming to mind recently in the US is near Boise, Idaho. They're actually implementing a treatment system in the Dixie Drain system, so an environmental water, where they found that they can remove phosphorus from the water source more effectively than they can at the wastewater treatment plant to get down to these really low levels. So this is an interesting case where they're actually looking at technologies in terms of the sink itself. All right? We can also consider this in terms of what form we're looking at. So if we're looking at this graphic, we have particulate matter on one end, soluble on the other, which is down on our bottom, might be cut off there, organic and inorganic. And if we map out the sources and sinks, they fall into different categories. And we can use that to help us think about how we can best manage these. So a couple things I'll point out on this graph are that most of our sinks wind up in this top left category in our particulate inorganic. But if we look at most of our sources, they fall in our bottom left and upper right category. So what are the differences between these and how does it help us to tackle the scenario? So I would find that this bottom category is kind of our good opportunity for total value recovery. So we have the phosphorus, but we also have the organics, the nitrogen, the potassium that we can get back out of this system. If we're looking at our upper right, this is our soluble inorganic form, so it's the easiest phosphorus to directly remove out of that system if we precipitate it. So we have an opportunity for pure products that might be passed on into the industry. And then if we look at our upper left corner, this I would say is our opportunity for water quality. So the others are going to address this too, but in this one we might actually be removing it out of the aquatic system. And this is definitely a big challenge here. This is very diffuse phosphorus. And so this is where I would go back to Steve's comment about don't focus on the trees. We're looking at the gaps in our space here. So this is an area where we don't have a lot of technologies or scenarios that can address this right now. So looking forward to sustainable phosphorus future, I think this is something that we should consider and keep on the plate. All right, so if we look at a toolbox of strategies where we can remove and recover, they might range anywhere through here, and different ones are going to be more economically feasible in different scenarios. So for example, if we're looking at fertilization, like Mike pointed out, we can look at very directed fertilizer to exactly meet crop inputs. So it might be a reduction conservation strategy. If we're looking, on the other hand, at high-intensity animal operations and food waste, again, lots of organics. So this opens up a good opportunity to recover and recycle. And this relates back to ongoing efforts like the EPA's Nutrient Recycling Challenge and Smithfield, for example. So if we can close that loop on the system, that's a really great value-added impact. Another example, so if we are looking at the sink itself in terms of lake sediments, so we heard about legacy P a little bit. If we have to deal with something like that, our options might be to sequester or remove that directly out of the sink itself. So kind of a few thoughts on this as we look forward towards what our technologies and our strategies for implementation of this sustainable future are going to be. I think one of the keys and the take-home messages here is that we're looking at total value proposition. So what are our products, what are our services, and also that technology alone is needed, but it's not sufficient. So we want to look in the broader context of the sustainability paradigm with environment, economics, and social considerations. And then, again, we're focused on the biggest return for investment. So where can we focus our efforts to get the best quality products that we can in terms of actual recovered products, but also primarily focusing on protecting the water quality of our environment. So in closing, I'm going to throw this graphic up one more time. And again, so here's our opportunities, but let's focus on skiing towards the spaces. So what I'd like, as we move into our break time in just a couple minutes, is for everybody to kind of think about in your own context and your own domain, where are the opportunities that you're working with? Do they fall into one of these spaces? Are they outside of it? And so as we continue this discussion from all of our different stakeholder perspectives, I think it's going to advance us as we continue to look forward at these future technologies. So with that, I will close, and if there's time for questions, we can take them.
Thank you, Brooke. Thanks, Steve, and you also for talking about skiing. It's very refreshing to think about skiing with today's weather and yesterday's weather. So it's a cool breeze is flowing. So questions, please, for Brooke.
All right, I have one. I already grabbed the mic, sorry.
Could you turn the mic on? I think it might be off.
Is that better?
Yeah, we need
okay.
it for the recording.
Yes.
So.
Okay, great. Great presentation, Brooke. If you can pull back the slide, the Cordell white block flow diagram. I had a question about the orange block.
Sorry, we'll get there in just, there we go.
Yeah, so can you talk about the non-ag soil and landfill block? What's going on there?
Okay, yeah, on this far side you're pointing to?
Yes.
Yeah, so in this simplified diagram, that one is just representing things that are not going into our waters in this case. So biosolids out of, if they're landfilled or other sources there, or byproducts out of our fertilizer processing that aren't necessarily going directly into the water space. Is that your question?
All right, there's one. Jim.
So my question is, in your graph that showed the particulate soluble and organic, non-organic, in that bottom left quadrant where there's value from several resources there, could you just maybe talk about, is the technology easy to, to strategically focus yourself on 3 resources versus, I just want the P and nothing else?
Yeah, I think it's a really good question. So, and I think the answer varies. So I think that there's some processes in place where we can harness them. So if we think about, for example, a digester, we know that we can get the energy out of it. As I've discussed at some point this morning, you know, the energy value of methane versus hydrogen is a different question, but that's also going to allow us to solubilize any of these nutrients in there. So we have the nitrogen coming out, the phosphorus coming out. But in traditional setups, they might not be arranged to necessarily capture those all together. So I think that our step forward is thinking about how we can co-capture those in a way where we're not necessarily releasing nutrients and having them clog up pipelines or things like that. So I think it's the perfect space to move into to think about how we can tackle multiple things of these at once.